Hey guys, welcome to the first video of module number 6. So this module will deal with the topic shear strength of soil. So let us begin with some very basic concepts. You know, in civil engineering we have got three types of failure. The first is tensile failure. Suppose I have got a body and I pull the body at both the ends. So that means I am applying tensile force at both the ends of the body. Now if the body fails because of this tensile load, the type of failure will be known as tensile failure. Now the same body, if it is subjected to compressive load, then the body may be crushed if the force is very high enough, and such kind of failure will be known as compressive failure or sometimes called as crushing failure. Now crushing failure is very much prominent in case of columns. Last is shear failure. So if I have got a body lying over a table, then let us assume that it is subjected to a horizontal force P. Okay, so because of the force P, the body may split into two equal halves or two different halves, and each part may slide in two opposite directions. Okay, the first part may slide in the left side and the bottom part may slide to the right side. So such kind of failure is known as shear failure. Now you see, because of the load P, equal and opposite force will be developed inside the body. This is because of Newton's third law of motion. That is, every force has got an equal and opposite reaction. So because of the shear force P, another force inside the body will be developed. Let us call it as Q. So the force P is called acting shear force. Okay, and the force Q is known as resisting shear force. Now the acting shear force will be generating a stress in the body, which is called the acting shear stress or the disturbing shear stress, and the resisting shear force will be generating a resisting shear stress. Now if the resisting shear stress is higher than the acting shear stress, then the body will be safe, it will not fail at all. But in case if the resisting shear stress or the resisting shear force is less than the acting shear force or acting shear stress, then the body will fail because of shear. Okay. Now an important point is, shear failure does not necessarily mean that the load is acting always in the horizontal direction. When you analyze a simply supported beam in toss, you assume that the load is acting vertically, right? And because of this load, you draw the shear force diagram. That means you are taking into account the shear stress because of this vertical load. Okay, so this is a very important point to be kept in mind. Now in soil, it is only the shear failure that is being observed. There is no tensile or crushing failure taking place in soil. So it is only and only shear failure that is prominent in a soil mass. So this brings us to a very important concept, and that is shear strength or shear resistance of a soil. So what is shear strength? It is the maximum shear stress that a soil can resist without undergoing any kind of failure. Okay, so that is the basic definition of shear strength or shear resistance. So shear strength in soil is developed because of three main reasons. The first is interlocking between the particles. You see, some soil, they have got a very rough and angular structure. So because of this, the soil particles, they perfectly fit with one another, and because of this a bond is developed, which ultimately results in the development of shear strength. So this is particularly observed in coarse grain soil where I have got gravel and sand. Okay, the second is intermolecular force of attraction or cohesive force. Now when I say cohesive force, I need to mention another term, which is adhesive force. So adhesive force and cohesive force. What is adhesive force? You see, when two particles of different materials are joined with one another, then it is known as adhesive force. So we have got adhesives in the market, for example Dendrite and Fevicol. So what they do, they join two different materials. For example, if I want to join a chalk with a duster, I'll be applying either Fevicol or Dendrite to either of them, and then I'll be sticking them together. So you see, adhesives help in joining two different materials. But when it comes to cohesive force or cohesives, the force of attraction is between same particles or same materials. Okay, so this is actually observed in clayey soil. So clayey soil develop shear resistance because of cohesive force. So cohesive force or cohesion, it is denoted by small c in soil mechanics. Okay, the next is frictional force. So frictional force also helps in development of shear strength. So this is actually observed in silty soil or silt. Now silty soil, they have got frictional force acting as well as cohesive force also. So silty soil develop shear strength because of cohesive force as well as frictional force also. Now let us try to understand the frictional force in more detail. So let us go to the basics of physics. So here you can see I have got a body. Okay, to this body I am applying a horizontal force P. Now this body, it will be having its own weight which will be acting in the downward direction. So let us assume that the force is acting in the downward direction, and if the mass of the body is m, then the weight of the body will be m into g. Okay, so the weight of the body is mg, which is acting downwards. Now because of this, another reaction force will be developing which is acting upwards, and we denote it by capital N, right? Anyway, so now if I try to push this body because of the force P, an opposite force will be developed which is acting between the body and the floor of the body. So this is actually F, and this is nothing but the frictional force. Okay, now one thing is very important, that is frictional force is depending upon the normal reaction or the weight of the body. You see, if the weight of the body is 2 kg, then the frictional force developed will be very less, and as a result of which I can easily push the body, right? Now the same body, if it is of say 200 kg weight, then the frictional force developed will be very high, and as a result of which the load that is required to push the body will also be very high, or it will be very difficult to push the body. So one thing I have established is that frictional force is directly depending upon the normal reaction. Now when I have got proportionality, I get a proportionality constant which is denoted by mu. Now what is mu? Mu is coefficient of friction. Now if you look into the diagram, you will see that the frictional force and the normal reaction, they produce a resultant force which is denoted by R. So this resultant force, it makes an angle phi with the normal reaction. So this phi is actually called as angle of friction, and from physics you know that coefficient of friction is equal to tan of angle of friction. So in the next step I have written F is equal to tan phi into n. So in the next step I have simply rearranged the terms, and I have got F is equal to n into tan phi. Now if I try to compare this equation with soil, then I will find that the frictional force is equivalent to the shear strength developed in the soil. So shear strength in soil or shear stress in soil is denoted by tau. So this is tau. Okay, and the normal reaction, it is equivalent to the total stress of the soil particles, which is denoted by sigma. So you have learnt in module 2 that total stress is denoted by sigma, and tan phi is left as it is, so we have written tan phi. So the equation for shear strength or shear resistance in soil is tau is equal to sigma into tan phi. Now I have told you that silty soil, they have got cohesion force as well as frictional force acting all together. So to this equation, what I will be doing is I will be adding cohesion in this case. So I have got the equation as tau equal to C plus sigma tan phi. So this is actually a very important equation, and this is known as Mohr-Coulomb equation. Okay, so let us discuss in more detail what is the Mohr-Coulomb equation. So here I have got the Mohr-Coulomb equation, that is tau is equal to C plus sigma tan phi. Now let us try to understand what each of these terms are. Tau, as I have already told you, it is the shear strength of the soil, and since it is a kind of stress, so the unit of tau will be kilonewton per meter square. C is cohesion or cohesive force. Sigma is total normal stress. Phi, in physics we call phi as angle of friction, whereas in soil mechanics we call it as angle of internal friction. C and phi together, they are known as shear strength parameters, because if you can calculate C and phi of a soil, you can actually calculate the shear strength of the soil. Sigma, it can be calculated if you know the density and the height of the soil mass. Okay, you have learned in module 2 that in order to calculate normal stress or effective stress, you simply need to know the unit weight of the soil and the height of the soil. Okay, anyway, so these are the terms of Mohr-Coulomb equation. Now later on it was found that the shear stress of the soil is not actually dependent on the normal stress or the total normal stress. It is actually depending upon the effective normal stress, which is denoted by sigma dash. So when I take the effective normal stress, the cohesion or cohesive force also becomes effective in nature. So this is called as effective cohesion, and the angle of internal friction is also known as effective angle of internal friction. So when I take the effective stress into account in the Mohr-Coulomb equation, then that equation is actually called as modified Mohr-Coulomb equation. Okay. Now for the time being, let us stick with the original Mohr-Coulomb equation. Okay. Now let us go back to mathematics. So in maths you have learned the equation of straight line. So what is the equation of straight line? It is y equal to mx plus c, where y is the y coordinate, m is actually the slope of the line, x is the x coordinate, and c is the intercept made in the y axis. Okay. Now if I compare the equation of straight line with the Mohr-Coulomb equation, I will find that y is equivalent to tau. Okay, m is equivalent to tan phi, that is slope, x is equivalent to the total normal stress, that is sigma, and c is kept as it is. Okay, so you can see I have correlated the Mohr-Coulomb equation with the straight line. So if I can correlate, obviously I can draw the line for Mohr-Coulomb equation, or I can draw the graph for Mohr-Coulomb equation. So on the right side you can see that I have got a graphical representation of Mohr-Coulomb equation, where I have taken tau on the y-axis because tau was equivalent to y, x was equivalent to sigma, that is normal stress, so I have taken sigma on the x-axis, right, and c was the intercept, so this is the intercept made on the y-axis. Now from the intercept I have drawn a straight line which is making an angle phi, so that the slope is tan phi. Okay, so this line, if someone asks you what is the equation of this line, this equation will be tau equal to c plus sigma tan phi, that is, it is the equation of Mohr-Coulomb, right? Now this line has also got a special name, and it is failure envelope. Okay, so let us try to understand the importance of failure envelope now. So now you can see I have got a footing over here, and below the footing there is soil mass, so I have randomly picked a point P. Okay, so if I ask you what is the state of stress at point P, then the answer will be something like this. Okay, so what is this? Let us try to understand. So this is actually the soil element. Okay, to this soil element I have got vertical stress, which is denoted by sigma 1. So this vertical stress is because of the load coming from the footing. Okay, so apart from that, I have got lateral stress acting on the soil mass, which is denoted by sigma 3. So why is this lateral stress coming? This is because this point P, or this soil at point P, is surrounded by other soil particles, right? So these soil particles will also exert pressure into the point P, and as a result of which I have got pressure denoted by sigma 3. So mind you that sigma 1 and sigma 3, these are actually principal stresses, something which you have learned in strength of materials. Sigma 1 is actually the major principal stress and sigma 3 is minor principal stress. So obviously it means that sigma 1 is greater than sigma 3. Now let us suppose that because of this stresses, because of sigma 1 and sigma 3, the soil fails due to shear along the plane AB. Okay, so AB is the shearing plane, and this plane makes an angle with the horizontal, which is denoted by alpha f. Okay, so the angle alpha f is actually known as angle of failure, right? Now here I have got two important equations. The first is the equation for angle of failure. So angle of failure is equal to 45 degree plus phi by 2. If you remember, phi is angle of internal friction. Okay, and the second equation is actually a relation between sigma 1 and sigma 3, and that is sigma 1 is equal to sigma 3 into tan square alpha f plus 2c tan alpha f, where c is cohesion. Okay, so these two equations are very important as far as numericals are concerned. Okay, now let us go back to the failure envelope and try to understand its importance. Okay, now you see, from the stress element, this is a plane which is the principal plane, because principal stress sigma 1 is acting on it. Now if you remember from strength of material class, there is no shear stress acting on a principal plane. So here I will be having only sigma 1 and no shear stress. Similarly, this is another principal plane where the minor principal stress is acting, and similarly I have got other two principal planes over here. Now when principal planes or planes are represented in terms of Mohr circle, they become points. Okay, so if I try to draw the Mohr circle for this stress condition, then it will be something like this. See, first I have got sigma 1 and sigma 1 is greater than sigma 3, and I have told you that each plane will become a point. So this plane is represented by this point. Okay, so this is sigma 1. Sigma 3 is minor principal stress, so it is less than sigma 1, so I have plotted somewhere over here. Okay, so this is sigma 3. So if I join sigma 3 and sigma 1, I can actually draw a Mohr circle. This circle can be completed in the downward part also, but since this is a symmetrical circle, so I have neglected the lower part and simply I have drawn the upper part. Okay, so this is how I draw the Mohr circle from the stress element. Now let us suppose that the load coming from the foundation is increased. So if the load coming from foundation is increased, obviously sigma 1 will increase. So now instead of having sigma 1 over here, I'll be having sigma 1 say over here. Okay, so now if I try to draw the Mohr circle, it will be something like this. Okay, here I have got sigma 3 and here I will be having sigma 1. So till now you can see that the Mohr circle is below the failure envelope. In both the cases the Mohr circle was below the failure envelope. Okay, now the stress from the footing is further increased. Okay, so sigma 1 has gone to another level, so here I have got sigma 1, but this time the Mohr circle, it touches the failure envelope. Okay, so when the Mohr circle touches the failure envelope, it means that the soil has reached its critical situation. When I say critical situation, it means that the shear resistance of the soil is exactly equal to the shear stress acting on the soil. Okay, Till now the soil has not failed, but it is at the critical stage. Now let us assume that the sigma 1 is further increased. So sigma 1 now goes to somewhere over here. Okay. So now if I try to draw the Mohr circle, it will be crossing the failure envelope and it will reach sigma 1. So you can see that the Mohr circle has now crossed the failure envelope. This means that the shear stress that is acting on the soil is higher than the shear resistance of the soil, and as a result of which the soil will now fail because of shear. Okay, so the bottom line of this explanation is that if the Mohr circle is below the failure envelope, the soil is safe from shear. But in case if the Mohr circle crosses the failure envelope, then this soil has actually failed by shear. In fact, such kind of Mohr circle does not even exist, because this will mean that the soil has failed. So you cannot draw the Mohr circle for such kind of situation. Okay, so this is the importance of failure envelope. I hope you have understood. So that's all for today. See you in the next video.